Hello everybody. In this lecture, I'll cover half of Chapter 15. In Chapter 15, we broaden our understanding of stellar properties, whereas in Chapter 14, we were mainly concerned with the Sun. Here we have an illustration of the Sun and the planet Earth, and we see the sunlight coming towards us. Something to note here is that as the sunlight's energy comes towards us, it becomes more diffuse. It becomes more diffuse. What do I mean by that? Well, as an example, you might consider a incandescent bulb. If you're standing very close to the bulb, it will be very hot when on. But if you're far away from it, even though it's on, you can see the light, but you don't feel the hotness. In a similar vein, as the sun emits energy, the amount of energy that surrounds the sun, say here, is the same amount of energy that surrounds the sun out here. But because it's distributed over a larger imaginary spherical surface, it's not as hot or as intense. But the luminosity is the same whether we talk about an imaginary spherical shell here or an imaginary spherical shell way out here. The amount of energy emitted per unit time is the same. Here we have the equation that relates what we've been just mentioning, namely the energy per unit time emitted by the sun being distributed over our imaginary spherical surface, 4 pi distance squared. And as we are farther and farther away from the source, in this case the sun, then this quantity, luminosity divided by 4 pi distance squared, gets smaller and smaller. Therefore, when it comes to receiving the sunlight from the sun, we don't receive the luminosity of the sun, that is the full energy emitted by the sun per unit time. What we receive is just a portion, a portion. And we can rearrange this equation if we want and write the equation below. The idea is that maybe we know the distance of some star of interest, and maybe we have measured its brightness, and therefore we can calculate its luminosity, how much energy it's giving off per unit time. Here's a nice illustration of what we've been talking about. Here are the imaginary spherical shells surrounding the sun, and notice that the energy that occupies this area is the same amount of energy that occupies this area, which is also the same amount of energy that occupies this area. And so as the energy spreads out farther and farther, though the amount of energy there is the same, it's spread out more and more, so it becomes more diffuse, and hence it's not as hot or as intense. As an example, if you're like some people, if you use the microwave, you might make it a point to stand far away from the microwave. And so this equation here tells us why standing away from the microwave helps. Remember, the brightness is proportional to 1 over distance squared. Brightness, or the amount of energy received per unit time, per unit area, is inversely related to distance squared. So if you double your distance from the microwave, you've cut the energy you're receiving down to a quarter. If you triple your distance from the microwave, then you're cutting the energy received down to 1/9. Here's an example. How would the apparent brightness of Alpha Centauri change if it were 3 times farther away? Well, again, brightness is proportional to 1 over distance squared. And so there's 1 over distance squared. So if I triple the distance, then I have 1 over 3 squared, so it's 1/9. And so the amount of um, energy being received per unit time per unit area, or the apparent brightness, will be 1/9 of the original or former amount. Alpha Centauri is the closest star system to the Earth. Next we come to parallax. And parallax is a practical way of getting a handle on the distance to stars of interest. And here you see the Earth at 2 different positions. For example, here in January, we might see the star of interest with respect to the background stars. But then in July, notice that that star moved. The amount by which it moved, we denote by this angle P here. This angle will be very, very small. With the naked eye, we would not be able to see this. We would not be able to see this. It wasn't until the proper telescopes were made could this be seen. And in this illustration, we have a few ingredients to help us infer the distance to the star of interest. We have the angle P here, which is maybe in arc seconds. And this is the distance to the star. And this is the distance to the sun. We have a nice triangle here. Using simple geometry, we can relate the 3 quantities to calculate distance. And that specific equation is this. The distance to that star of interest is the 1 divided by the angle. The distance to that star of interest is 1 divided by the angle. Now the angle here is going to have to be in arc seconds, and the distance is going to have to be in parsecs. If you want to convert from parsecs to light years, you just have to multiply by 3.26. Or in other words, 3.26 light years corresponds to 1 parsec. And the word parsec just means parallax of 1 arc second. Parsec means parallax of 1 arc second. As an example, if p is just 1 arc second, 1 divided by 1 is 1, and so the answer would be d is 1 parsec. Here we have a very pretty picture. We see a lot of jewels in the sky, but actually they're stars with different colors. And if it's wintertime and you go outside and you look at the shoulder, or one of the shoulders of Orion, you notice that Betelgeuse has a reddish hue. And if you look to the right of Orion, you'll notice that Aldebaran also has a reddish hue, unlike many of the other surrounding stars. This tells us that stars, you can classify them in terms of temperature. And also, you can classify stars in terms of their luminosity, how much energy they're emitting per unit time. And here, you're told that the most luminous stars is 1,000,000 times larger than the luminosity of our sun. 1,000,000 times more luminous than our sun. The least luminous is 1 part in 10,000. The least luminous is 1 part in 10,000, the solar luminosity. And here it looks like we're looking at stars near the center of the Milky Way, so a lot of stars. When we talk about brightness, we might be referring to the apparent magnitude. Apparent magnitude. And there's a nice relationship between the brightness of stars to what we call the apparent magnitude. Apparent magnitude is just a classification scheme. And for example, the sun has an apparent magnitude of about negative 27. The faintest objects that the Hubble Space Telescope can see is plus 30. What this tells you or us is that the brighter the object, the smaller the apparent magnitude. And the more faint the object, then the larger the apparent magnitude. So again, the sun's apparent magnitude would be negative 26.7 because it's pretty bright. And the Hubble telescope, the faintest objects that it can see is plus 30. As an example, suppose you're looking at two objects and the difference in apparent magnitudes is 5. The difference in apparent magnitudes is 5. Well, in that case, you'd have 5 divided by 5 is 100. So this just means that the brightness of star 2 is 100 times the brightness of star 1. And here we have absolute magnitude. This is just basically apparent magnitude at distance of 10 parsecs. Again, absolute magnitude is just apparent magnitude at a distance of 10 parsecs. Here we come back to classifying stars, and we're told that the hottest stars are 50,000 Kelvin, coolest stars 3,000 Kelvin. The sun's surface is 5,800 Kelvin. And you might remember that this number, about 6,000 Kelvin, corresponds to about 10,000 degrees Fahrenheit. A question for you is, which of these stars would be the hottest? Would it be the reddish stars, or would it be the bluish stars? As a clue, you might think about your oven. If you have maybe a heating coil on top of your, say, your stove, or even if you're looking at, say, the heating rod in the oven, when you turn on the stove or the oven, you'll notice that the color of the heating element changes. It's first red, and if it gets hotter and hotter, it turns orange. And if it gets really, really hot, it can turn yellow. And if you keep going hotter and hotter, which, we don't go that far, you would go with the red, orange, yellow, green, blue, violet. So the red end is cooler, and the blue end is hotter, which I guess is kind of counterintuitive. Because when we think of blue, we think of maybe water in the sky, and so that's kind of cool. But yeah, so blue is hotter and red is cooler. Here is what we call a spectrum, and different stars are classified according to their temperature. And the temperature scheme is given here, O, B, A, F, G, K, M. The authors in Cosmic Perspective tell the reader to have the mnemonic O, be a fine girl or guy and kiss me to try to remember. O is the hottest and M is the coolest. Our sun is a G type of star, So again, O is the hottest, M is the coolest. And in the spectrum, it's kind of similar to if you shine white light through a prism. If you were to do so, you would just get the rainbow, red, orange, yellow, green, blue, violet. But here, instead of just getting the full color spectrum, you have some missing pieces. And the reason why is because elements in the star are absorbing certain portions of the spectrum. And so that gives each star a unique spectrum because the temperature will determine the spectrum itself. So notice, for example, with hydrogen being present in stars, I notice that the absorption is very faint with the O star, but very stark with the A star. So again, with hydrogen, notice that the absorption is very faint, but very stark with the A-type star. Here we have a question, which kind of star is the hottest? M would be the coolest here. F is in the, just above G, which again is the sun. K is down here, so A would be the hottest. Also keep in mind when we talk about main sequence stars, we're talking about stars that give off light by fusing hydrogen. Again, main sequence stars refer to stars that generate light by fusing hydrogen. Here we have what are called the Harvard calculators. Harvard calculators. And this is Edward Pickering, who is in charge at the Harvard Observatory. And the goal of these Harvard calculators were to map and classify stars. Amongst them, we have Annie Jump Cannon. She was a suffragist. She is credited with classifying stars via their spectra. She is the one who is credited with classifying stars via spectra, which is just what we mentioned back here, right? Thinking of stars in terms of their spectra. And also, she believed that this spectra correlated with the temperature. And a person here, which I'm pointing to, Cecilia Payne-Gaposchkin, if I'm pronouncing the name correctly, she came later and showed that that belief is correct. The spectrum does correspond to temperature, but importantly, she explained why. And she did it via something called ionization theory. So as an example, if you come back here with hydrogen, notice the absorption is very weak with the O versus, say, A-type star. The reason why is because the high surface temperature of O stars, implies weak hydrogen lines because most of the hydrogen has already been ionized. That is, there are no electrons present to partake in this absorption. Next, we come to identifying stars. During winter months, you probably notice the brightest star in the nighttime sky, and that would be Sirius A, but we just say Sirius typically, right? And if you're in the southern hemisphere, that you would see it, I guess, in the summer months, whereas in the northern hemisphere we see it in the winter months. And here you see two stars because Sirius A actually has a partner, which we call Sirius B. And Sirius B is a white dwarf, which is what our sun will become in the future. And we'll talk more about that later. A white dwarf is not a main sequence star. The reason why it's giving off energy is because it is just very hot. It's only giving off thermal energy. It's just very hot. So no fusion is taking place. White dwarfs are on the order of the size of the Earth, but the mass is about the mass of the sun and very, very dense. And looking up at, say, Sirius A and noticing that it wobbles, even without seeing Sirius B, you know then you can infer that it must have a partner. And here you see that the period of the dance between the two stars is 50 years. So if you go through these photos, notice 1950 replicates 1900. So again, the period is 50 years. About half of all stars are in binary systems. About half of all stars are in binary systems. Another way of detecting stars is through these what we call spectroscopic method. The spectroscopic method. So we just mentioned the visual. Now we use spectra, colors. The idea is that when a star is moving towards us, the color spectrum or its unique color spectrum will be blue shifted. And when the star is moving away from us, if we're down here observing, and when the star moves away from us, then the spectrum would be redshifted. So you see that here. So notice that the top colors are, or excuse me, the absorption lines are red shifted. Excuse me, blue shifted. That is, they're shifted to the right. And on the bottom, notice they're shifted to the left. So notice here. So up here is blue shifted. The absorption lines moved to the left relative to here, where they move to the left here. Up here to the right, down here to the left. So you can see here this one, this one, this one, this one. A third method is using eclipsing binaries just by looking at the apparent brightness over time. So here you see both stars A and B, and so you see a certain amount of brightness, a certain amount of energy delivered to you per unit area per unit time. Here again, you would see the same thing. Um, in the fourth picture, star A is totally hiding star B, and so you're not getting both sources. So naturally, there's a dip. In picture 2 here, notice that you're getting both of them. You're getting both of them, but not all of A here. This is a way to calculate masses of stars of interest. You can use Newton's version of Kepler's third law. And I'll remind you that g is the universal gravitational constant whenever gravity is involved. P is the period of orbit. A is the semi-major axis. So again, if you know the period, so for example, for Sirius A and B, the period was 50 years. And if you know, say, the distance, maybe using parallax, you can then go about calculating masses here. Next, we come to the HR diagram, or the Hertzsprung-Russell diagram. I want to draw your attention to some things here. So I guess it's kind of, so maybe it's come here. Well, I guess first I'll just point out some things. Notice that you have luminosity versus temperature. The hotter the object, the more so to the left you are. So O, B, A, fine girl, or gal, or guy, excuse me, and kiss me. The main sequence stars form a diagonal. This is where the hydrogen fusing stars are located. You have white dwarfs. Again, our sun, which is over here right now, will one day come down here. Here we have giants like Aldebaran, which is in the constellation Taurus. Our sun will one day come up here before it comes back down here after it runs through its hydrogen. And you have supergiants like Betelgeuse, for example, and Antares, which you can see in summer months in the northern hemisphere. You have Deneb, which is in the Swan constellation. Arcturus and Aldebaran were like our sun in the past. Aldebaran and Arcturus were like our sun in the past, fusing hydrogen. And in the future, our sun, when it becomes a giant, it's going to possibly engulf Mars, or excuse me, engulf the Earth. Um, but if we had Betelgeuse and Antares at the center of our solar system, they would engulf Mars and the asteroid belt. Betelgeuse and Antares would engulf Mars and the asteroid belt if they were at the center of our solar system. And um, yeah, so they're pretty huge. The second brightest the second brightest star in the night sky is here, Canopus. So here's a nicer picture. Notice some things here. So again, here's the temperatures: 30,000 Kelvin down to 3,000. Oh, be a fine girl or guy, kiss me. And here's the G-type star, our sun. Notice you have the masses of the stars. Notice that the higher luminosity stars have higher masses. So the higher mass stars are like prima donnas, basically. They run through their fuel very quickly. And for that reason, their lifetime, you can see, is about 10 million years. 10 million years for these prima donnas up here. But notice our sun, which is over here at a lower temperature, it doesn't run through its fuel as quickly, and so it lives longer at about 10 billion years. But then you come down to red dwarfs, they live a long, long time. Here, when it says solar units, as an example, 1 means equal to the solar luminosity, or our sun's luminosity. 10 to the 4 means 10,000 times our sun's luminosity. 10 to the negative 4 means 1 part in 10,000 our sun's luminosity. Coming back to our sun here, our sun will one day exhaust its hydrogen in its core, having turned hydrogen into helium. Then it will shrink and fuse a hydrogen shell around its helium core, increasing its size, that is, becoming a subgiant and giant. The pressure builds until the helium fusion in the core occurs, increasing the radius of the sun further to Earth's orbit. And then, as it sheds its outer layers, it becomes a white dwarf, which is no longer fusing anything, is just very hot and emitting thermal radiation. And so in the very, 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 very distant future, it'll just be a black dwarf because it won't be emitting anything. And our sun will be a giant in the future, 7 billion years from now. 7 billion years. Again, when it comes to white dwarfs, they're about the size of our sun, about the mass of our sun. The density is huge. It's about 1,000,000 times more dense than water. 1,000,000 times more dense than water. When it comes to classifying stars, we mentioned the temperature, but we can also classify with luminosity, where 1 means the most luminous and 5 means the least luminous. As an example, the sun we say is G25, so G is, again, that tells you the temperature. G2 just means it's cooler than G1, but hotter than G3. Betelgeuse is classified as an M-type star, so it's not as hot as our sun, but still very, very luminous. Very, very luminous. So notice it's very luminous, but the temperature is low compared to our sun. So it's huge compared to our sun. Remember, we said it'll reach out to Mars and the asteroid belt, but it's cool. That makes sense because we mentioned the light bulb, and we said the farther you are away from the light bulb, the cooler it is. So same thing with the Betelgeuse. Since it's so large in radius, its temperature is lower. And here we have a question: which star has the largest radius? Well, radius runs larger as you move diagonally here, northeast on this illustration. So just think back again with Betelgeuse. So remember we said high luminosity, low temperature. So what you want to think about is that incandescent bulb. It's very hot, but since you're far away from it, the temperature is low. And being very far away from it means a large radius. Okay. Or in other words, the energy is distributed over a larger area.